Excuse me, Dr. Russell, before you begin, I also have a question.
Go ahead.
For module 1A, I never saw a submission link to turn in our work for that module.
Hold up. Let me go to Blackboard right quick because we got a couple of minutes before we actually start. So let me pull up Blackboard because actually I was supposed to go in this weekend, but I didn't. I took a break. But I'm gonna actually delete one of those handouts in 1A. But I gotta figure out which one it was. Hold up. Let me see. Too many classes. Okay. Yeah, this is the submission link right here. Can you hold up? My bad. Let me share the screen again. Can you see my web browser now?
Yes.
Yes,
Yeah.
we can see it now.
So the submission link is going to be right here where it says resonance.
Okay.
Yeah. And then you can just, since we are like in 1A and kind of finishing up, you can put everything in this one. I'm going to close this one. And then you can just put everything in one place. And then I'm going to edit this and take off one of these because we really only worked on one of these handouts. I was supposed to clean this up earlier, but I didn't. My apologies for that.
Will you keep the extra credit spots? I know I turned something into that folder, or do you want us to condense it?
Did you put it here?
Yes. Well, no, the it said functional group extra credit, the one that we did with the big molecule.
Yeah, right here. Yes.
Yeah.
I think that's an assignment. Yeah, you can put it right there. You can just either, because I know it's lumped in with all the other sheets, but you can screenshot it and upload it.
I had accidentally submitted one of my worksheets to a different submission link, if that makes sense. But I wrote in the notes like which worksheet is which.
Uh-oh.
I think it was for the functional group. I put in a different folder, and then
Did you put it in one?
No, I put everything from module 1A. If this is, are we in module 1A right now?
Yes.
Yeah, everything from module 1A, I put it in module 1A. It's however, I put it in a different submission link. Like for the FC groups, I think I submitted a different worksheet for one of the worksheets that we had for module 1A, if that makes sense.
I'll have to go in and look. Just shoot me an email and kind of put that in writing. And then when I'll go in to grade this stuff, I'll go check it out.
Okay.
Yeah.
Dr. Russell.
Go ahead.
What's your email? Because when I try to send your email, it said I couldn't do it. It's
Really?
on Blackboard.
Yeah, hold up. Let me just put it in the chat. All right. Any other questions before we jump back in? All right. Okay. So we left off on Friday asking about or talking about intermolecular forces and talking about and you should have gotten a video describing the different intermolecular forces, van der Waals and dipole, and hydrogen bonding, so on and so forth. So anybody got it yet?
You said the
Says-
boiling point. Oh, you go ahead.
I think maybe 174 to 176 degrees Celsius.
Okay, so we're gonna say 176 degrees Celsius. And then what about the boiling point for the ketone?
It was 163 degrees Celsius.
$163. All right, so when you compare that, you can see a huge difference, right? This is easy. This is a better comparison just because these are all liquids. So it's hard to get a melting point for something that's already a liquid. But the point is the intermolecular forces are going to cause differences in the physical properties. So the lowest boiling point you see is the fluorooctane. It's 142. And then the other one is 163, and then the alcohol boils at 176. What that means is that it takes more energy to get that alcohol to boil. And everybody understands what's happening when something is boiling, right? Molecules are colliding together. You know, that you increase their energy, they start to vibrate, and then they change states from a liquid to a gas, right? And start escaping in the form of a gas. But with that alcohol, since it's able to hydrogen bond, right, those alcohols are held together a lot more tightly. And because they're held together a lot more tightly, it takes a lot more energy to get them to vibrate, break apart, and eventually get converted from liquid to gas. Now, when you look at the two, the fluorooctane and the octanol, when you look at those two, there's a 21-degree difference in the boiling point, but they're both like held together by dipole-dipole interactions, right? There's a dipole between the carbon and fluorine. There's a dipole in the carbonyl. Why do you think that's such a big difference in those two, if they're both dipole? And we're talking about the intermolecular forces holding these compounds together. Remember, this is a flask full of 4-octanol. So all those molecules are interacting with each other, and their dipoles are lining up with each other. Same with the the fluorooctanol. So what do you think is the cause of that big difference in the boiling point?
Is it because of the double bond and the oxygen?
That's part of it, because here with fluorooctanol, right, there's a dipole. It's a big dipole too, because fluorine has an electronegativity of 4. So it's got a big dipole right here. But if you look at that ketone, right, you can actually draw a resonance form where that carbon has a full positive charge, right? So if I do this like that, I can actually draw that and show a full positive on carbon. I'm just going to abbreviate that, where this is fully positive and not just partially positive. So that's probably the reason why you see that big difference, because that dipole is a lot stronger for the ketone than it is for the fluorine. Even with fluorine having an electronegativity of, of 4, right? There's a huge dipole because of that pi bond between carbon and oxygen, and you can actually draw the resonance form and show carbon as a full positive. So that's going to be a really strong attraction between those molecules, right? Compared to a 4-fluorooctanone, where the dipoles are going to line up, yeah, but you don't have it, you won't ever have a full positive, even though that partial positive is pretty strong, is not the same as having a full positive. So that's why you see the difference in temperature between those two, even though both of them are held together by the exact same intermolecular force. Is that making sense?
Kind of.
All right, let me cut it so I can write that down. Let's see if I might have to just cut all of it. And remember these intermolecular forces, again, the stronger the intermolecular force. Add a page. Like the stronger the intermolecular force, the more it's going to affect the physical properties. All right, let me erase this. All right, so we said with the alcohol, that has the highest boiling point. Right, so what you're comparing again is the intermolecular forces that are holding these things together. Right, so that has the highest boiling point because of the hydrogen bonding. And then we can say with the ketone versus the fluoride, the ketone has a higher boiling point. Due to a stronger dipole. Right. And it's probably due to the fact that that carbonyl can do resonance and put a full positive on carbon, like so. All right. Any questions about that? Is it, if it's not clicking, say something. So what you're doing in these particular cases is you're looking at molecules, you're looking at what intermolecular forces are present, and you can basically make an assumption based on those intermolecular forces that are present, you know, you can make an assumption about their physical properties. Right? If you compare something that is held together by hydrogen bonding to something that's held together by simply van der Waals, then you can make the assumption that the hydrogen bonding molecule is going to have a higher boiling point, or is going to have a different melting point or freezing point, so on and so forth. So let's look at the next set of examples, because these are all van der Waals. Everything here is van der Waals. Like all these molecules are held together by van der Waals forces. Because again, van der Waals forces are present in all molecules. Doesn't matter what functional groups they have. But here, these are all alkanes. And let's go ahead and cut this. Let's do that. And I'll white out what we don't need. right? So here again is asking to compare the boiling points, even though every one of these molecules is only held together by van der Waals forces, right? We don't, and to be clear about van der Waals forces, those are based on what we call these micro dipoles. Like, so all these carbon hydrogen bonds have, let me draw in a couple. Right, all your carbon hydrogen bonds that are here have dipoles because of the slight difference in electronegativity between carbon and hydrogen, but they don't have huge dipoles, right? So none of these are polar covalent bonds. And so when you look at that overall, if you have a bunch of these little micro dipoles, and I think I mentioned this in the video, it's almost like Velcro, right? So the positive parts are going to line up with the negative parts. And if I have another molecule underneath here, right, and it has the same micro dipoles, right, you can see right away that the partial negative right here is going to pick up on that partial positive right there. All right, so it's going to pick up on that, and it's going to be the same thing as you stack these things on top of one another. All right, so that's what's holding them together, those little partial dipoles being attracted to one another. And it's like, again, it's like a strip of Velcro, right? And when you look at these and they're not any other functional groups, what you start having to think about is the surface area. Right? Surface area, the size, and the bulk. Right? So surface area, size, bulk, and symmetry. If you have a lot of symmetry, then those molecules are going to be able to pack tighter. If you don't, then they don't pack as well, and there's a lot of room between them. So you'll see differences in the boiling point and the melting point and things like that, right? These molecules are what we call saturated. Right, so no pi bonds. These are all alkenes. I'm sorry, not alkenes, alkanes. Hope I didn't say alkenes earlier because I know I said that word, but they're all alkanes. So saturated means that every space on that carbon is filled in with a hydrogen or another bond to carbon. So no pi bonds, all sigma bonds, right? So this will also give us a little bit of another chance to do a little nomenclature. So let's take this molecule right here because we're going to look up the boiling points, and then we're going to compare them, and then we're going to figure out why one is lower than the other. So let's do that, or higher than the other. So 1, 2, 3, 4, 5, 6, 7, 8. That's my backbone. 8 carbons is octane. That's the parent. Where are the substituents located on that? Anybody? Have I already found the longest chain? Anything that's not in the longest chain is on it.
Third and
Is it 5 and 6?
So right here and right here. Good. Now, that you said 5 and 6. That's great. I'm with you. But when we get ready to name it, we got to count from this end, because it gives those substituents lower numbers. Right?
So you don't count from the right side every time.
Yeah, not every. No. You can count the number of carbons. That's fine. But when you get ready to name it, you want any of your groups, your substituents that are attached to the chain, you want them to have the lowest number possible. So you want to always start counting from the end that's closest to that first branch point.
Okay.
That's a great question. And we haven't covered nomenclature. I just sneak it in when I can because there are a lot of rules and a lot of conventions, and that can get real boring, like real fast. So I just sneak in nomenclature when I can. So we know the parent is 8 carbons, is octane. It's got 2 groups, one at 3, one at 4. What are those groups? What's the end of every line in a skeletal form if it's not some other atom?
CH3.
CH3, good. So this is a CH3 right here. This is also a CH3. And we call those, when they are acting as substituents, we call them methyl groups. Without, if it was a CH4, we call it methane, but because it's attached as a substituent, we call it a methyl. All right. So we have a methyl at 3 and at 4, and the parent is octane. And whenever we have 2 of the same groups, which we do here, right, both of those are methyls, we just stick a prefix in front of the name of the substituent. So this is 3, 4 dimethyl octane. Right? Can somebody look that up? 3, 4 dimethyl octane. Look up the boiling point. We're looking at the boiling point because that's more than likely a liquid also. Most of your alkane, long chain alkanes are liquids.
One 163 degrees Celsius.
Can you say that one more time?
163 degrees Celsius.
163. All right. I'll take that. All right. Let's do the next one. We have a method now. Let's find the longest chain. 8 carbons. If we count and end at any of these other ones, it's not going to give us 8 carbons unless we count here, which is symmetrical. It's not going to change anything. So either direction, the green or the pink, doesn't matter. It's 8 carbons. I like the pink route because I'm weird and the last carbon is pointed down, and I like that. So, but that's okay. So our parent here is going to be octane. Again. And this is, how many methyl groups are attached here? 1, 2,
4.
3, 4. Good. Excellent. And which end are we going to count from? Let me see if you caught that on the last example.
The right.
From the right. 1, 2, 3, 4, 5, 6, 7, 8. Excellent. So how many? We got a methyl at 2, 3, 4, and 6, right? And we got 4 of them, so we need a prefix. We need and the Greek prefix tetra means 4, just like di means 2, mono means 1, tri means 3, tetra is 4, penta, hexa, hepta, so on and so forth. All right. So this is 2, 3, 4, 6. Tetramethyl octane. All right. Can somebody look up the boiling point for that? It's probably going to be a lot lower than the 3,4 dimethyl octane. And if you can't find this particular isomer, just look up tetramethyl octane, because the boiling point is probably going to be similar for any of those isomers.
I got 184.7 degrees Celsius. That's just for the tetramethyl octane. That's not the two.
Okay, we'll take it. And then look up the boiling point for just plain octane. 184. Interesting. It's explainable though.
The boiling point for octane is 125 degrees Celsius.
Okay, great. So now we can explain why we see what we see, right? Intuitively, you would think that the tetramethyl octane would be would have a much lower boiling point than the rest of them, simply because it's so bulky, right? All those groups are, all those substituents are on there and it's bulky. But sometimes, again, if you have symmetry, then it allows even those bulky groups like that to pack, because this is all about packing, how these things stack on top of each other. And so if it has the highest boiling point, what that means, and it's got the same number of carbons in the backbone, so the surface area is slightly different because of the groups, but it's not that much different. But since it has those groups, and there is not necessarily symmetry, but there's a little bit of, how do I put this? You can see how those methyl groups on the top part of the backbone can kind of help those molecules to line up with each other, right? If we think about, instead of stacking them vertically, like if we stack them horizontally. So if we put one here like this, and then we put another one right next door to it, like this, right? You can think about those molecules stacking that way. And the fact that they can do that, right, that's and stack well, that's what's going to increase that boiling point, right? The point you can see, okay, so this is 163, this is 125. You can see a similar pattern with those methyl groups. So you would have, if you stack them, instead of trying to stack them on top of each other, you stack them side by side, you can see how you'd be able to pack those in. Oh, sorry. Right? So with the octane itself, when you heat this up, it'll be easier to drive those apart than it is to drive these apart. And that's probably due to a little bit of symmetry again with those groups. If you have symmetry, for some reason, it allows those molecules to pack better. And the better packed they are, the more energy it's going to take to move them apart. Now, normally you would think, like with those groups and the added steric bulk, that they wouldn't pack well, but that little bit of symmetry between those two carbons allows those molecules to pack just a little bit better. So that's why the boiling point is so much different. Right, so what you're looking for, again, surface area, which is the same for all of them, because the backbone is 8 carbons, size, bulk, and symmetry. So in these two cases with the 2,3,4,6 tetramethyl and the 3,4-dimethyl, that's a symmetry issue, right? Those pack better because of the symmetry that's created by the methyl groups that are on the chain. Let's see if we have, let me see. Somebody look up 2-methyl octane. Let's see what the difference is between that and octane. Actually, look up 2,2-dimethyl octane. And let's see what we get there.
I got 156.1 degrees
So-
Celsius.
156.
156.1 degrees Celsius.
Okay. So 156 degrees Celsius. So again, you probably have a similar phenomena happening there too, with the 2,2-dimethyl octane. Again, there's symmetry on that one carbon, and that's going to allow for those molecules to pack better. That's interesting though. One of these, I think the 2,3,4,6 is the actual additive in gasoline to prevent knocking. Like that's what the rating on the gas 87, 89, 93, that rating is based on how much of this compound is in there, that 2,3,4,6 tetramethyl octane. All right. Any questions about physical properties? Any questions about intermolecular forces? Any questions about any of that?
So you made a comment about all of them being van der Waals. I
Van der
think.
Waals, yes.
What is the indication that it's van der Waals?
Because there are no other functional groups present.
Gotcha. Okay.
Yeah, it's all just carbons and hydrogens, right? If you have a alkane, like something like this, without any ketones or aldehydes or alcohols or acids or esters or any other functional groups, then it's only going to be van der Waals, because van der Waals is endemic to all molecules. Everything experiences that. But the only time you start experiencing hydrogen bonding or dipole-dipole interactions is when you have other functional groups that can create those situations. So if you don't have a functional group that's present that can create a dipole, or that can create or that can do hydrogen bonding, then it's all van der Waals. Move that down too. That's a good question. All right, other questions? Any other questions? Trying to line this back up how it was. All right, no other questions about anything? If not, we can stop and we'll pick up. What we're gonna do, I'll fix that later. Let me put that back because that's sloppy. What we're gonna do is on Friday, we're gonna start dealing with pKa and acidity. So we'll pick this up on Friday. And then we'll work in some other examples dealing with intermolecular forces, but we'll do it in the context of looking at pKa and other things like that. So with that being said, we're going to stop here. We'll pick up Friday, and I'll see y'all then.
It's not necessarily a question about any of the information. I had already, like the assignments that we had in Blackboard.
Yep.
I had actually already uploaded them from like what we've already done, and then this one we just added another part to it, like what we went over today.
Yeah.
Do I need to like resubmit it or not worry about?
No, no, you can leave it because this is going to be on the second test.
Okay.
So what
Okay.
I'll do is I'll put another link in 1A just for this part.
Okay.
Yeah,
Okay.
and then module 2 with which is PKA,
Mhm.
that'll have its own submission links.
Okay.
Yeah, I'll fix it because I realized that, it's like the modules kind of overlapped. So, but we'll be good. Don't worry.
Okay. Okay. Sounds good.
All right.
Thank you.
Okay.
So I have a question.
Sorry.
So we don't turn it in, and so we turn in now, like, or tomorrow, like all of this, like 1A, like all of the problems that we just did.
Yeah, but the fact that the not functional groups, the intermolecular forces and all that stuff is and functional groups too, is on the second test. If you turned in what you already had up to that point, that's fine. If you haven't, then go ahead and submit it. But you're going to end up resubmitting this part for the second test. But go ahead and turn in what you have.
So we can officially start module 2 now.
Yeah. Did I already send the PKA videos out?
No.
All right. I'll send them today when I post the notes and stuff. All right. Any other questions? All right. I'm gonna send out PK videos today for Friday, so help you get ready for that. Go ahead and download the let me look into and see what that handout looks like. I think I consolidated this one so we won't have the same problems from 1A. Let's see. Yeah, it's only one handout. So go ahead and download the handout for PKA that's in the assignments folder in the second module. And, Friday, have that with you so you can start filling it in. And I'll send the videos out and I'll post the notes and I'll post this video as well. All right, if there are no other questions, I'm gonna go ahead and stop.